In early May 1945, a British naval task force centered around the heavy cruiser HMS Norfolk was being hunted. The escorting destroyers were actively pinging the depths with sonar, sweeping the ocean for the remnants of the German U-boat fleet. But beneath their acoustic net, something entirely new was moving. According to Schnee's later account, U-2511 reached an undetected firing position against a British force in early May 1945. Yet the boat fired nothing and turned away. This is the central paradox of the Type 21 U-boat. It was one of the most consequential submarine designs in naval history. Its submerged performance alarmed the victorious Allies and helped shape the first generation of Cold War submarines. Yet, this revolutionary machine achieved exactly 0 combat kills. How did a warship so advanced it reset global naval power end up missing the war it was built to fight? The answer is not a story of flawless foresight. It is the story of a desperate industrial hack, a submarine built for an impossible engine it never received, and a production program that sabotaged its own navy. To understand the machine that changed the world, we must rewind to 1943, to a moment when the German fleet was bleeding to death. May 1943 went down in the archives of the Kriegsmarine as Black May. In May alone, more than 40 U-boats were lost across the wider campaign, including more than 30 in the Atlantic. For Admiral Karl Dönitz, the commander of the U-boat fleet, the casualty reports were not just a string of tactical defeats. They were mathematical proof that his primary weapon system had become fatally obsolete. To understand why the German fleet was suddenly facing extinction, it is necessary to strip away a lasting myth. The infamous Type 7 U-boats that had terrorized Allied shipping for 4 years were not true submarines. They were submersibles. The distinction was deadly. A submersible was essentially a surface torpedo boat that only went underwater to launch a brief attack or to hide. Its entire existence was governed by the limitations of diesel-electric propulsion. To cross the ocean and hunt, the boat relied on diesel engines, which required a massive, constant supply of atmospheric oxygen. Therefore, a U-boat spent the vast majority of its patrol operating exposed on the surface. When it finally dived, the diesel engines had to be shut down. The boat then relied on heavy lead-acid batteries to power electric motors. But these batteries were physically small, and the underwater electric motors were weak. A submerged Type 7 could sprint at about 8 knots for barely an hour before its batteries ran dangerously low, or it could creep along at a walking pace to stretch its endurance. Once the power was exhausted, the boat had no choice but to surface, restart the diesels, and charge the batteries all over again. For the first half of the war, the U-boats used the night as their armor. They surfaced under the cover of darkness to charge their power banks and attack as high-speed surface raiders. But by 1943, Allied technology stripped that armor away. The mass deployment of airborne centimetric radar meant that a British or American patrol plane could track a surfaced U-boat from miles away, through heavy clouds, and in the dead of night. A U-boat crew, blindly charging their batteries at midnight, would suddenly be caught in the blinding glare of an aircraft's searchlight, followed seconds later by lethal depth charges. The tactical equation had completely inverted. To surface was to invite instant destruction. Yet, to dive was to invite slow suffocation as the batteries drained. Dönitz was forced to withdraw his shattered fleet from the North Atlantic. The existing German fleet could only be kept alive through a patchwork of interim measures: heavier anti-aircraft armament, radar warning equipment, revised tactics, new weapons, and the snorkel, which allowed diesel charging at periscope depth. But Dönitz knew that fighting an aviation war from the wet deck of a submersible was a losing gamble. The old rules of naval warfare had collapsed. If the U-boat force was to regain the offensive, it had to permanently sever its tether to the surface. Dönitz did not need a better submersible. He needed a true submarine, a vessel designed from the keel up to live, fight, and sprint entirely underwater. The traditional naval establishment had no immediate solution, but an eccentric hydrodynamic engineer named Hellmuth Walter claimed he already had one. Years before the disaster of Black May, a small, bizarre-looking vessel slipped into the waters of the Schlei Inlet in northern Germany. It was the spring of 1940. The submarine, designated V-80, completely lacked the cluttered wooden decks, anti-aircraft platforms, and jagged conning towers of the operational fleet. It looked less like a traditional warship and more like a perfectly smooth silver torpedo. When the V-80 submerged, naval observers were entirely unprepared for what they witnessed. The prototype reached an underwater speed of more than 23 knots. It was moving faster beneath the waves than most conventional military escorts could travel on the surface. The man behind the design was Hellmuth Walter. He was not a traditional naval architect bound by shipyard conventions. He was a brilliant engineer obsessed with hydrodynamics and the physical limits of underwater power. Walter recognized that the slow, unaerodynamic shape of traditional submersibles was simply accepted because their weak electric motors could never push them fast enough for water resistance to matter. If a submarine could somehow generate massive horsepower while submerged, it could adopt a highly streamlined shape to slice through the deep ocean. The fundamental problem was oxygen. Massive horsepower required combustion, and combustion required air. Walter's radical solution was air-independent propulsion. Instead of relying on the atmosphere, Walter's engine would carry its own chemical oxygen supply. In Walter's hot cycle system, highly concentrated hydrogen peroxide, known as perhydral, was decomposed into steam and oxygen. That oxygen supported the combustion of a separate fuel, producing the hot gas that drove the turbine without drawing air from the surface. Walter had effectively engineered a peroxide-powered, air-independent turbine submarine. The tactical advantage was staggering. If a submarine could sustain 20 knots underwater, the entire Allied convoy system would collapse. The U-boat could reposition ahead of a convoy, shorten the escort's reaction time, and make a destroyer's sonar attack far more difficult. But it would not be untouchable. By 1943, as Allied aircraft decimated the surfaced U-boat force, Admiral Dönitz desperately championed Walter's concept as his only hope. The Naval Command authorized a massive, full-scale combat vessel, the Type XXI. Walter's team drafted a colossal, aggressively streamlined hull, designed specifically to house the enormous chemical fuel bays required for the perhydral turbine. But the revolutionary engine contained a fatal trade-off. Perhydral was volatile, corrosive, dangerous to store, and extraordinarily resource-intensive to manufacture. Germany's bomb-damaged electrical grid and chemical industry could not support the refining capacity required for an ocean-going fleet. Without fleet-scale perhydral, the Type XVIII appeared finished. But two senior naval architects, Friedrich Schürer and Klaus Bröking, refused to let the project die. Unlike Walter, they were not propulsion visionaries. They were pragmatic ship designers, deeply familiar with the brutal constraints of wartime construction. As they studied Walter's colossal, teardrop-shaped hull, they fixated on its internal geometry. To accommodate the massive amounts of liquid chemical fuel required by the turbine, Walter had designed an unusually deep, cavernous lower section into the submarine's frame. Schürer and Bröking asked a radical question. What if they kept the perfect hydrodynamic shape, ripped out the impossible chemical turbine, and filled those massive, empty fuel bays with standard lead-acid batteries? Historically, naval architects viewed batteries as necessary dead weight, heavy, dangerous, and strictly limited in capacity. But this was a desperately brilliant industrial pivot. Traditional U-boats also wasted power pushing their flat decks and heavily armed hulls through the water. Walter's form offered a far more efficient platform for the enlarged battery system. Schürer and Bröking calculated that by using a brute force approach, packing the lower hull with roughly 3 times the battery capacity of a standard U-boat, they could power dramatically upscaled conventional electric motors. The trade-off was clear. They were abandoning the unlimited, sustained underwater sprinting of Walter's chemical turbine. Standard batteries would still eventually drain and require the submarine to raise a breathing tube or snorkel to run its diesels. But the immense electrical reserves, combined with the frictionless hull, would allow the boat to surge to 17 knots for over an hour, or creep silently at 5 knots for an unprecedented 2 to 3 days. It was no longer a rocket sub, it was an Elektroboot, officially designated the Type XXI. When Admiral Dönitz reviewed the proposal in June 1943, he immediately recognized its strategic value. The genius of Schürer and Bröking's pivot was that it required no theoretical breakthroughs. It relied entirely on proven, existing electrical technology, merely scaled up to an unprecedented volume. It completely bypassed the impossible chemical supply chain. Dönitz championed the design to the highest levels of the German state, securing immediate approval. But the institutional demand came with a staggering catch. Because the Allied anti-submarine forces were actively slaughtering the existing fleet, building a handful of prototypes in a traditional shipyard would not turn the tide. The Naval Command required hundreds of these new submarines, and they demanded them instantly. This impossible quota would soon trigger a fatal collision between the meticulous craftsmanship of traditional shipbuilders and the blunt force of mass production factories. Approval left one structural problem unresolved: how to house the enlarged battery banks without widening a conventional pressure hull and sacrificing the streamlined form. The architects solved this by discarding the concept of a single steel tube. Instead, they engineered a pressure hull with a figure-8 cross-section. They effectively stacked 2 massive structural cylinders on top of each other. The upper cylinder contained the living quarters, the torpedo room, the diesel engines, and the electric motors. The lower, deeper cylinder was devoted entirely to the mountain of batteries. When wrapped together inside a smooth outer steel casing, the 2 stacked cylinders gave the Type XXI a deep, cavernous belly, while maintaining a perfectly sleek, knife-like profile from the outside. But achieving 17 knots underwater required more than just raw electrical power. It demanded the ruthless elimination of parasitic drag. What made the Type XXI genuinely different from anything before it was what the designers explicitly chose to remove. For decades, U-boats had carried large, heavy deck guns to sink unarmed merchant ships on the surface, without wasting expensive torpedoes. Schürer and Bröking stripped away the traditional deck gun, while retaining enclosed anti-aircraft mounts in the streamlined tower fairing. They enclosed the anchor capstans and mooring cleats beneath flush steel plates. They smoothed the jagged conning tower into an enclosed hydrodynamic fin, leaving absolutely nothing on the outer skin to catch the rushing ocean. The internal architecture was equally revolutionary, specifically in how the submarine delivered its weapons. In older U-boats, reloading a torpedo tube was an exhausting manual process of pulleys, chains, and brute crew strength that could take up to 20 minutes per weapon. During that time, a U-boat was effectively disarmed and highly vulnerable. The Type XXI introduced a powered torpedo handling system. Torpedoes were moved laterally on their supports and driven longitudinally into the 6 bow tubes, allowing the crew to reload a second 6-torpedo salvo in about 5 minutes and a third within roughly 20. That gave the boat a formidable burst of firepower before it had to break contact. Yet, every major design choice solved a tactical problem while exacting a severe operational cost. The figure-8 hull successfully housed the massive battery installation, but it created an incredibly deep draft. The immense submarine rode deeply in the water, sharply restricting its ability to navigate shallow coastal straits and complicating its movement in and out of traditional naval bases. Even worse was the boat's behavior above water. Its long, deep hull, pronounced tumble home, and low surface metacentric height gave it poor surface seakeeping. In moderate swells, it could roll heavily, battering the crew and making external deck work hazardous. The designers accepted the penalty as a consequence of the new doctrine. The Type XXI sacrificed surface behavior to optimize submerged performance. The design was complete on paper. Building it under a daily rain of Allied bombs was another matter. To force the approved design into rapid production, despite the exposure of coastal yards such as Bloom and Voss in Hamburg, responsibility for delivering the fleet was handed not to a shipbuilder, but to Otto Merker, a production executive drawn from the automotive and fire engine industry. Merker looked at Schürer and Bröking's complex figure-8 blueprint and decided it could not be built using traditional naval methods. Laying down a keel in an exposed coastal dry dock and slowly building a hull upward took too long and presented too large a target. Merker imposed a radical, decentralized production mandate. The Type 21's pressure hull would be assembled from 8 principal prefabricated sections, with other structures and fittings produced separately. The massive sections, ranging from the torpedo room to the massive diesel compartments, would be fabricated deep inland, distributed across dozens of steelworks and heavy machinery factories far from the vulnerable coast. Once the heavy internal equipment was pre-installed, the massive steel rings would be loaded onto barges, floated down the rivers, and delivered to the coastal shipyards for rapid final assembly. On paper, the strategy offered a brilliant advantage. Dispersing the manufacturing protected the work from air raids, and simultaneous factory production theoretically promised to launch submarines in a fraction of the traditional time. But experienced coastal shipyard engineers fiercely opposed Merker's plan. They understood the unforgiving physical reality of deep-diving pressure hulls. A steel tube designed to withstand the crushing, uniform weight of the ocean at 500 feet could not be riveted together like a commercial truck chassis. The figure-8 design already complicated the structural integrity, and the engineers warned that inland factories, unaccustomed to naval architecture, could never achieve the millimeter tolerances required for a submarine. The Armaments Ministry ignored the shipyard warnings and ordered the modular program forward. The conflict between the factory and the shipyard soon became a physical disaster. When the inland factories began shipping the completed modules down the rivers, the coastal shipbuilders stared at a catastrophic failure of manufacturing tolerance. The inland steelworks, struggling with unskilled labor and rushed quotas, lacked the extreme precision of naval engineering. The massive sections arrived warped and misaligned. When cranes lowered the 8 modules onto the slipways to be joined, the edges of the thick pressure hulls often failed to sit flush. Pipes, cables, and other systems crossing the section boundaries could also arrive out of alignment. To prevent the submarines from crushing under water pressure, the coastal shipyards had to essentially rebuild the inland modules from scratch. Highly skilled shipyard workers were forced to deploy heavy winches and hydraulic jacks to physically bend the warped steel rings into alignment. They spent hundreds of thousands of labor hours cutting, refitting, and re-welding the botched steel sections. Merker's dispersed system, intended to save time, instead forced the coastal yards to absorb extensive rework and became one of several major bottlenecks in the program. Beyond the rework, design changes, transport disruption, shortages, defective workmanship, and continued bombing further constricted the program. By the time the shipyards produced seaworthy boats, the promised armada had become a trickle entering a war already in its dying days. On the 30th of April, 1945, the Type 21 finally went to war. Under the command of highly decorated U-boat veteran Adalbert Schnee, U-2511 slipped out of the heavily fortified concrete pens in Bergen, Norway, and headed into the North Sea. Out of a staggering production order that once promised hundreds of boats, U-2511 became the only Type 21 generally credited with completing a genuine operational war patrol. For Schnee and his crew, the patrol required a complete break from years of surface-running tactical instinct. Veteran submariners who had spent the war fighting from the open, wind-swept bridge of a surface-running submersible now found themselves sealed inside a deeply submerged steel tube, entirely dependent on complex acoustic sensors to map the world above them. The boat also entered service with unresolved defects. Its advanced hydraulic systems, which drove the torpedo reloaders and diving planes, were plagued by leaks and mechanical failures, while the immense battery banks demanded meticulous maintenance to prevent explosive hydrogen buildup. Crews had barely enough time to learn those limits. Yet, beneath the mechanical defects, the submerged design performed as intended. In early May, just days after departing, U-2511 made contact with a British hunter-killer group centered around the heavy cruiser HMS Norfolk. This was exactly the kind of heavily armed escort screen that had systematically slaughtered the old German fleet over the previous 2 years. Instead of breaking contact, Schnee pushed the electric motors and surged toward the formation. He later claimed that U-2511 used its submerged performance to close the range. The speed could reduce an escort's reaction time and complicate ASDIC tracking, although it increased the submarine's own noise and did not render Allied sonar blind. According to his account, the boat passed through the screen and reached an undetected firing position broadside to HMS Norfolk. He could have launched a devastating spread of hydraulically loaded torpedoes, dived deep, and outrun the inevitable counterattack. But the torpedoes remained in their tubes. Hitler had died on the 30th of April. On the 4th of May, several days later, Schnee received Dönitz's order to cease offensive operations. For his boat, the fighting was over. Schnee was testing his ship, not fighting a battle he knew was already lost. Having demonstrated what the new boat might be capable of, if his later account is accepted, he ordered U-2511 away and returned toward Bergen, leaving the British formation apparently unaware of the encounter. U-2511 returned to port without firing a shot in anger. But when Allied intelligence dismantled the captured fleet, shock replaced relief. In the weeks following the surrender, Allied naval intelligence teams descended upon the captured German ports to inspect the surviving remnants of the U-boat fleet. British, American, and Soviet engineers opened the hatches of the Type 21, crawled through its figure-8 pressure hull, and examined the captured blueprints. Allied assessments recognized that an earlier, reliable Type 21 force could have created a grave new anti-submarine problem. Whether it could have reversed the Battle of the Atlantic remains an unprovable counterfactual, especially given the design's reliability, training, maintenance, and production defects. But a submarine optimized for sustained submerged operation threatened escort doctrine built around slower, surface-dependent boats. What the Allies dissected and ultimately copied was not a piece of magical science fiction. They did not discard Hellmuth Walter's hydrogen peroxide turbine immediately. Britain tested a captured Walter boat as HMS Meteorite and later built further peroxide-powered experimental submarines before danger, complexity, and the rise of nuclear propulsion brought the line to an end. Instead, they studied and adapted the practical ideas embodied in the Type 21, its massive electrical capacity, reduced hydrodynamic drag, snorkel operation, underwater first doctrine, and rapid weapon handling became important reference points for the next generation of submarines, but not an exact technical template copied in every detail. The United States Navy took its captured Type 21s back across the Atlantic, tested them relentlessly against their own destroyers, and immediately initiated the Guppy program, the Greater Underwater Propulsion Power Program. The Americans took their victorious fleet of World War II surface-running submarines, violently stripped away the deck guns, sealed the external cleats, smoothed the conning towers into aerodynamic sails, and packed the lower hulls with radically upscaled battery banks. They adapted the German emphasis on streamlining, snorkel operation, greater battery capacity, and submerged performance while developing the Tang class, the first new American design intended to improve upon the Type 21 rather than reproduce it. On the other side of the Iron Curtain, Soviet designers absorbed captured German research and incorporated many Type 21 ideas into their post-war requirements. The massive Whiskey and Zulu class fleets that later confronted NATO were strongly influenced by the German boat, but they were Soviet designs shaped for different missions, industries, and operating doctrines. As nuclear propulsion began to emerge, American and Soviet submarine designs rapidly diverged. Hellmuth Walter had given the world the shape of the future, but Schürer and Bröking had given them the internal architecture that actually made it possible. Today, the physical legacy of that desperate industrial gamble rests quietly in the German port city of Bremerhaven. The Wilhelm Bauer, originally commissioned in early 1945 as U-2540, sits peacefully in the water as a preserved museum ship. It is the last intact Type 21 remaining in the world. Walking its narrow, meticulously engineered steel decks today makes the boat's underwater-first design tangible. That architecture, not its brief wartime service, became part of the foundation of the modern submarine.